Modulus. The modulus of a real number x is written as a bar, an x and a bar, is the distance from the origin to the point x on the real line. So we have seen these lines before in maths, and these lines represent length or distance, but in this case, when we talk about the modulus, it's specifically the distance from the origin. And you'll see this again in another chapter called complex numbers. So the modulus of 5 is equal to 5. The distance from 0 to 5 is 5. So you could say 5 or 5 units. The modulus of minus 3 is 3. The distance from 0 to minus 3 is 3. So for example, if we're at 0, which is the origin, and we move across to 5, we are moving a distance of 5. If we're at 0 and we move back to minus 3, we are moving a distance of 3, or 3 units. The mathematical definition of the modulus is as follows. Definition of the modulus of a real number. If x is an element of R, then the modulus of x is x if x is greater or equal to 0, or minus x if x is less than 0. For example, the modulus of 5 is equal to 5 as 5 is greater than 0, while the modulus of minus 3 is equal to minus 3, which gives us 3 because a minus by minus is a plus, as minus 3 is less than 0. The modulus of x can also be called the absolute value or the positive value of x. The graph of the modulus function f of x maps to the modulus of x is y equals the modulus of x. To construct this graph, we can make the following table of values. So minus 4 made positive is just 4, minus 3 made positive is just 3, minus 2 made positive is 2, minus 1 made positive is 1, 0 stays as 0, 1 is already positive, stays as 1, 2 stays as 2, 3 stays as 3, 4 stays as 4. Plotting these coordinates on our x and y axis, we have, first of all, minus 4, 4, which is here. Then minus 3, 3, which is here. Minus 2, 2. Then minus 1, 1. And 0, 0. 1, 1. 2, 2. 3, 3. And 4, 4. And obviously we could keep going in either direction. So it looks like a V shape or a downward arrow shape, and it's important to learn this off by heart. So you want to be able to recognize straight away that this is the graph of y equals modulus x. So notice that it has its apex or its minimum point at the origin 0, 0. And then it is a diagonal line that cuts right through the positive quadrant of our x-axis, or the first quadrant, and the second quadrant. So it basically bisects the 90-degree angle that is formed by the x and y axis on either side. So completely bisects this 90-degree angle, which means it cuts it in half. Now consider the function f of x maps to the modulus of x minus 2, and its graph y equals x minus 2. So if our x value is minus 2, then we're going to have minus 2 minus 2, which is minus 4, and the modulus of minus 4 is 4, so that's where the 4 comes from. If we have an x value of minus 1, it's going to be minus 1 minus 2, which is minus 3, and the modulus of minus 3 is 3. If we have 0, it's going to be 0 minus 2, and the modulus of minus 2 is 2. If we have 1 minus 2, we're going to get 1, and the modulus of 1 is still just 1, and so on. So these are our x values, these are our y values. So if we want to plot them on our x, y axis, we have minus 2, 4, which is here. Then minus 1, 3. Then 0, 2. Then 1, 1. Then 2, 0. Then 3, 1. Then 4, 2. 5, 3. and 6, 4. So we join them together with a ruler, and obviously they go on in either direction to infinity. So it's very similar to the graph of y equals the modulus of x, which we just had a look at. It's the exact same actually, except it's been moved 2 places to the right. It's been translated 2 places to the right. So now the minimum point of our graph is at 2 on the x-axis instead of 0, as it was with the graph of y equals the modulus of x. So if we have minus 2 inside the modulus, we are going to have our minimum point at 2. If we had minus 3 inside the modulus, we would have our minimum point at plus 3. If we had minus 4 inside the modulus, we would have our minimum point at plus 4. Likewise, if we had plus 2 inside the modulus, we would have our minimum point at minus 2, and so on. So from the graph, we can see that the graph is V-shaped. The graph has its apex, or its bottom corner, on the x-axis, at this point here, which is 2 on the x-axis. So if x minus 2 is equal to 0, then x is equal to 2. So this is where our modulus apex is. So as the modulus of x minus 2 is equal to x minus 2, for x minus 2 is greater or equal to 0, i.e. x is greater or equal to 2, so bringing the minus 2 over the inequality sign and getting plus 2, or minus times x minus 2, for x minus 2 is less than 0, i.e. x is less than 2. The graph y equals the modulus of x minus 2 consists of the line y equals x minus 2 to the right of the apex, and the line y equals minus times x minus 2, minus by x is minus x, minus by minus 2 is plus 2, so we get y equals minus x plus 2 to the left of the apex. So we have the line y equals x minus 2 to the right of the apex, so this is the line y equals x minus 2. And then we have the line y equals minus x plus 2 to the left of the apex. So this is the line y equals minus x plus 2. And putting them together, we get y equals the modulus of x minus 2. The expression, the modulus of x minus 2, can be interpreted as the distance from the point 2 to the point x. So remember, distance is the key word here. The graph y equals the modulus of x minus 2 can be considered to be the image of the basic modulus graph y equals the modulus of x under a horizontal translation of 2 units. So basically we have the graph of y equals the modulus of x, which goes here, and it's been moved 2 units to the right. So the minimum point, or the apex, of the graph y equals the modulus of x is 0, 0. So the minimum point, or the apex, of the graph y equals the modulus of x minus 2 is at plus 2. Likewise, suppose we want to construct the graph y equals the modulus of 2x plus 3 without making a table of values. So we could always choose x values, let's say from minus 3 up as far as 3, sub them into our equation and get out some y values. But if we don't want to do that, determine the position of the apex, which is the minimum point or the corner, on the x-axis by solving 2x plus 3 is equal to 0. So we're going to minus 3 to both sides, so we get 2x equals minus 3, and divide by 2 on both sides, so we get x is equal to minus 3 over 2. The apex is therefore going to be minus 3 over 2, comma 0. So if this is x, and we had let our equation equal to 0, then this is our x value, and 0 is our y value. So the apex, or the minimum point of our graph, is minus 3 over 2, comma 0. So here's our x-axis, and this is minus 3 over 2. So minus 1.5. Next, we construct the line to the right of the apex. So we have y equals 2x plus 3. So swapping the x for 0, you get y equals 2 times 0 plus 3. 2 times 0 will cancel out. So we get y is equal to 3. So by taking 1 point to the right of the apex, so for example, 0, 3, so an x value of 0, we subbed in an x value of 0, and we got out a y value of 3, so we've got x is 0, y is 3. Construct the line to the right by joining the apex to the point 0, 3. So go to 0 on the x-axis, 3 on the y-axis, plot a point. Then we're obviously going to join those together with a ruler. Next, we're going to construct the line to the left of the apex. So we have y equals minus 2x plus 3. So minus times 2x is minus 2x, minus times 3 is minus 3. So we have y equals minus 2x minus 3. Again, we're going to take 1 point to the left of the apex. So let's say we sub in x is equal to minus 3. We'll end up having minus 2 multiplied by minus 3 minus 3. Minus 2 by minus 3 is plus 6, and 6 minus 3 is plus 3. So we get an x value of minus 3, a y value of 3. Construct a line on the left by joining the apex to the point minus 3, 3. So go to minus 3 on the x-axis, 3 on the y-axis, plot our point, join them together, join the apex to the line, and continue it on as far as you want on your graph. It doesn't have to stop at those 2 points.